Alrighty, good afternoon, folks. Today, we're going to pick up where we left off on Monday. And that was talking about combinations of functions. So I'll remind you the basics. So I want to give a nice careful treat of the material that we're covering. I also want to make sure that we cover everything that you guys need for your current homework. And there is 2.8 stuff on your homework, I believe. So we need to do that. This is section 2.7. So we're going to finish that up. And then we're also going to talk about one-to-one functions. And their inverses. So a lot of stuff to cover today, which means there isn't a lot of time to play around or work extra things. Are you hearing a loud buzzing or blowing sound in the background, Ronald?
Yeah.
So I apologize, that's my computer's fan. It's currently processing the video from my last class. Can you still hear me?
Yeah, but like barely, it's like super low.
Let me see if I can pause this. So I told it to stop. No, I can't pause it. Right. That should do the job. Just give it a second and that noise will go away. There we go. All right. So last time, we said given two functions, f and g, we can form the functions f plus g, f minus g, f times g, f over g, and f circ g. We could also say g circ f, although it's a little redundant, by the rules that f plus g of any number is what you get by taking f of that number and adding it to g of that number. So if I ask you to find f plus g of x, you say that's f of x plus g of x, and then you plug in for these formulas and add them up. F minus g of x is f of x minus g of x. F times g of x is f of x times g of x. F over g of x is f of x divided by g of x. F circ g of x, or f of g of x, is f of g of x. And g circ f of x is g of f of x. These first few had some convenient rules for their domains, but really the only thing you need to remember is to watch out for domain red flags. So if you need to find the domain of a function, you can use that rule that says take the overlap or take the overlap and throw away what makes the bottom 0. But really the thing to do is just write the function down, whatever it is, and then look out for domain red flags. These are variables downstairs in a fraction, or variables under an even root. Right, and in each of those cases, we need to make sure that the problems are avoided. So if you've got variable stuff in the denominator, you need to make sure those aren't 0. And if you've got variable stuff under an even root, you need to make sure that that stuff is greater than or equal to 0. I want to talk a little bit about machine diagrams. So you guys may remember the function g can be thought of as a machine, right? It takes in some inputs that might look like x, and it sends out some outputs that we call g of x. You've probably seen this diagram before, right? It's a common tool in algebra classes when we describe just exactly what a function is. It's a machine that takes in x's and then spits out some modified form of that, which we call g of x. You could take the machine for g and the machine for f and put them next to each other on the assembly line. So as the input for f, I use g of x, then what will come out? Well, I'm taking in g's and I'm doing f to it. What comes out is always f of the input. So it would come out here as f of g of x. What I've just drawn for you, this whole thing where you stitch the output of the one machine together with the input for the other, is the big machine diagram for the composite function f of g of x. All right, so I have an analogy that will work here, but it's a little bit gross. Are you ready? Fog, this composite function, f of g, is the human centipede of functions. G gets his ass end sewn on to the input for f. I know it's gross. Human Centipede might be an old enough movie that you guys don't know what I'm talking about. You guys know what I'm talking about? I don't want to get any more explicit than that. So fog, f of g of x, takes your input x, does g to it, and then takes that output and puts it in as an input for f. So that's the human centipede thing. The output for g becomes the input for f. So the ass of g is sewn to the mouth of f, and the result is this composite function. Domain rules for composite functions are a little bit more complicated. Last time I gave you some domain rules for each of these. They should be in your notes. I'm not going to write those down again. The domain of f of g of x, if you think about what you have to do to be able to feed something to this function, x, in order to be in the domain of this, must be in the domain of g. So is a subset of the domain of g. So you take the stuff that you could use as an input for g, those things are possible elements of the domain of the composite. That's as much as I want to say about the domain of the composite, because from there, it gets a little bit complicated. But I do want to get practice. And the rule for all of this stuff, guys, really is the same as they were in college algebra. You just watch out for those red flags. The trick is, especially with these last three, you write down the function and then you don't simplify. Don't cancel anything. So to find the domain, of any combined functions first, write out the formula for the function it's not really a step, but I like to write it in here as a step to help remind us. Don't simplify. Especially don't cancel any variables. Then look for red flags. Okay? A handful of your homework problems this week just give you a function f, give you a function g, and ask you to mash them together in all these different ways, and then find the domain. And the domain of each of those combined functions. So I want to run through a few exercises like that, and we might as well take them from your homework. You notice also that the first quiz and study guide are up. Remember the rules for that. The quiz, you're going to go and take it like a quiz. And then after you're done, you're going to review your answers and write out nice, neat, perfect solutions to each problem. Those nice, neat, perfect solutions are what you're going to submit in Canvas. I'll show you here. Go to assignments. You go to, oh, do I not have your study guides in here? Oh, shit, we need to put those in. You guys have study guides, right? Oh, no. Okay. Yeah, so the study guides, I'm sorry, I forgot. I changed this because we're doing things online now. So the study guides, you don't even need to worry about as far as grades are concerned. All the credit's going to come from the quizzes. But you should write out those nice, neat solutions. And you're no longer required to submit them on Canvas, but talk to me about them. Yeah, that's the idea. The purpose of what I usually do here, instead of just having the grade here come from the quizzes, is have you submit study guides. But I forgot, since moving to online, we're not doing that. So just treat it like it looks. The homework is homework, the quizzes are quizzes, and the exams will be exams. But I recommend that you write out solutions to those problems and talk to me about them in office hours or via email so we can be sure that you're really comfy with everything. Okay.
Okay, so we're not submitting the study guide to Canvas anymore, right?
No, I'm sorry. Yeah, when I told you that on Monday, I was thinking of how I used to run the class. But since switching to online, I haven't been doing that with 1140 classes. So you're not required to scan and submit those like we talked about last time.
Okay.
Just required to do the quiz and WebAssign. But I still encourage you to write out solutions and email them to me or talk about them with me in office hours to make sure that you're comfy.
Okay. Sounds good.
All right, so that makes your lives a little bit easier. Let's take a look at this problem here. This first problem is a good way to just see how we're feeling about the notation. No, don't do that, just do this. So I'll leave the graph up there. This is homework 4, problem 1. We want to use the graphs to figure out f plus g of 0, f minus g of 0, f times g of 0, and f over g of 0. These all go the same way. You start with the definition. F plus g of 0 is f of 0 plus g of 0. And then you look to your graph and ask, well, what is f of 0? Can anybody looking at this graph tell me what f of 0 is? Don't leave me hanging.
For which one, F or G?
F. Yeah, what is f of 0?
0, 2.
Yeah, right? So you look along, you find the point on the graph whose x value is 0, and that y value is f of 0. So f of 0 is 2, plus what's g of 0?
4.
4, right? Yeah, same thing. We find x equals 0 and go up to the graph of g. That y value there is 1, 2, 3, 4. So f plus g of 0, this new function evaluated at 0, would be 6. What about f minus g of 0? Well, that should be f of 0 minus g of 0. F of 0 we said is 2. G of 0 we said is 4.
What?
2 minus 4, which is negative 2. Allison, did you have a question?
Oh, no, I'm so sorry. No, my computer just keeps messing up. I was yelling at it, so sorry.
Oh, that's okay. Yeah, I understand. F times g of 0 would be f of 0 times g of 0. F of 0 again is 2. G of 0 again is 4. So this would be 8. And f over g of 0 is f of 0 over g of 0, which is 2 divided by 4, which is 1/2. While we're here, and because the next few questions are very similar, could anybody tell me what f minus g of 2 is? So same graph.
It's 3 minus 5.
Good. So we'd begin by writing this as f of 2 minus g of 2. And then we look on the graph to find f of 2. Let's see, f of 2 is 1, 2, 3. And g of 2 is 1, 2, 3, 4, 5. So 2 minus 5 is correct. That's negative 2. Do we feel comfortable with this notation? Are there any questions about how we're getting these? If you do find yourself stuck or uncertain, remember to write this step. Instead of trying to go straight from here to here, if you write this in-between step, that will help you kind of regroup your thoughts. And one thing I find people do a little bit is too much too often. So go ahead and give your brain a break. Let the paper remember for you. What am I doing? Oh, I want to find f minus g of 2. That's the same as f of 2 minus g of 2. And then one at a time, you can go back and look rather than trying to do everything all at once. Okay, 3, 4, 5, 6, 7, 8. Let's do one more. Let's find f over g of 8. So if I wasn't immediately sure what to do, I would say, all right, well, this is the same as f of 8 over g of 8. All right, that's what I would write down no matter what, just to get started. And then I look on my graph. I go over to x equals 8, 1, 2, 3, 4, 5, 6, 7, 8, that's here. F of 8 is 1, 2, 3. And g of 8 is 1, 2, 3, 4. So this is 3 over 4. Nothing too hard, right? So you have plenty of questions like this, where I give you a graph and ask you to come up with some stuff. There's a little bit of describing functions verbally. Let me see, 13. So let's do another example here, but this time let's play around with composite functions. Suppose f of 3 is negative 7 and g of negative 7 is 5. Can we find f circ g of 3 or g circ f of 3? So one of these I've given you enough information. The other one I have not. Between the two, let's call them A and B. Which one do we have the information we need?
For A.
I think it may be helpful to start by writing this not in the circ notation, but in the regular function notation. So this is f of g of 3, and this is g of f of 3. To get started on part A, I would figure out what g of 3 is, and then try to plug that into f. But I don't know what g of 3 is. So not enough info is given for this. In other words, you kind of work from the inside out here, right? We have to figure out what g of 3 is and then figure out what f of that would be. But all I know is that g of -7 is 5 and f of 3 is -7. So this guy, I can't figure him out. What about this guy? How would we get started here? Well, it's g of something. What is f of 3?
-7.
Yeah. So this thing is g of -7. You see, I just figured out what the inside is. I left the outside alone. And then g of -7, I was told that that's 5. Do we understand how we're coming up with the answer in part B? Are there any questions about this, the notation, or where things come from? Composite functions are one of those places where I really don't trust college algebra professors to have done enough. So I'm trying to make sure we have a solid foundation. Everybody's good with why we don't have enough info for this one and why this one is 5? Make sure I'm not missing anything in the chat here. Oh, I see. Yeah, let's see. Do it again, please. All right. Okay. Yeah, let's look at another example. This time, let's make it just a little bit different. Here, I know. This time, I'll give you a table. So I'll write down a table for f of x. And I'll write down a table for g of x. And then I'll ask you for a few things. All right. So if I wanted to just play around or make sure we're comfy with function notation, I could ask you, what is f of 1? What is g of 0? So who can help me out? What's f of 1?
2.
2, right? Because when x is 1, f of x is equal to 2. In other words, f of 1 is 2. Okay, what is g of 0?
3.
Very good. What is f circ g of 3? How do I get started here? So as with the other similar problems, we should start with the definition. That's f of g of 3. And then we work our way from the inside out. G of 3 is 0. So whatever this is, it's f of 0. And then f of 0 is 3. So yeah, this is 3. What about g of 1? Here I would say this is g of 1. The inside part here, g of 1 is 2. So this is g of 2. Oh, but then g of 2 is 1. So this goes back to 1. All right, let's do one more. Let's do g of f of 1. Here I've got 3 functions composed, but the same rule works. Schematically, this would be g of f of 1. And we have to first sort out the inside, which is f of 1, the very most inside thing. So whatever this is, it's g of f of, and then what is f of 1? F of 1 is 2. So this is g of f of 2. Okay. But what's f of 2? That's 0. So this is g of 0. Okay, and what's g of 0? That's 3. Not too bad, right? Any questions on this example? Okay. Then I want to start looking at some of these domain problems, and we'll start gently, combinations with domains, and we'll ratchet it up as we go. So for this next guy, you have several problems like this in your homework. I'm going to let f of x be, how about just x minus 1? And g of x will be x over x plus 3. I want to find f plus g and f times g and f over g and their domains. So to get started, f plus g of x is f of x plus g of x. Which is x minus 1, because that's what f of x is, plus x over x plus 3. All right, this first piece is f, the second piece is g. And now we look for red flags, exactly. So what red flags do we see? Does this piece have any red flags? Yeah, no red flags from the x minus 1, just the x plus 3 in the denominator. So I need to figure out where that's equal to 0 and then kick that out of my domain. Good. So x plus 3 equals 0 when x equals negative 3. So our domain is all real numbers except negative 3, which in interval notation is negative infinity to negative 3 unioned with negative 3 to infinity. And again, sketching these is a really good idea. If you want to make sure you did it right, draw your number line. Here's negative 3. I'm allowed to be anything but that. So that's everything that's to the left of negative 3 and everything that's to the right of negative 3, but not negative 3 itself. A cool trick is the number of union symbols in your interval notation will be the same as the number of numbers that you punched out. So here there was one number that we punched out of the real line, namely negative 3, and I have one union symbol in my interval notation. Any questions on this process for finding the domain or this process for finding the algebra formula for the function? All right, if not, I'm going to continue here. F times g of x. Well, that's always f of x times g of x. F of x, again, is just x minus 1. And g of x is x over x minus 3. And we have the same red flags. So like we said in class on Monday, the domain of f plus g, f minus g, and f times g are always the same. So the domain's the same. Negative infinity to negative 3, unioned with negative 3 to positive infinity. It is, yeah, sorry, I wrote minus 3 there. Yeah, plus 3. Good catch, thank you. Now, if I wanted to, I could simplify this a little bit. I could write this as x minus 1 times x all over x plus 3. Are we all comfortable with that algebra? I treat x minus 1 as itself over 1, and then I multiply the fraction straight across. And there's no harm in doing that. Let's move to f over g. So this is the first place things can get a little bit tricky. f over g is f of x over g of x, which is x minus 1 divided by x over x plus 3. And here we do need to be more careful. Remember, my rule is don't simplify, right? Write down the formula, don't simplify, then look for your red flags. The reason I don't want to simplify is because right now I've got two red flags. I have the x plus 3 downstairs in the little fraction, and then I have x over x plus 3 downstairs in the big fraction. So here there's two red flags. Hammy, no. No, Bubba. Be good. So in the little fraction, I have the same domain red flag. So x cannot be equal to negative 3. We also have x over x plus 3, god damn this pen, downstairs in the big fraction. A little fraction, sorry, my pen is dying. Little fraction, and here this is big fraction. So I'm thinking of this as the little fraction and the whole thing as the big fraction. I have the x plus 3 in the denominator of this little fraction. That's a red flag because it's a variable in the denominator. And then I have this whole apparatus downstairs in the big fraction. So I need to make sure that this thing isn't 0. So I need x over x plus 3, the whole thing, to not be 0. And when is that whole thing going to be equal to 0? What do I have to watch out for? What would make x over x plus 3 equal 0?
Negative 3.
Negative 3 would make the bottom here 0, but I'm trying to figure out what makes this whole thing 0.
0.
Yeah, 0, right?
Yeah.
So x cannot be equal to 0 also. So my domain here is all real numbers except x equals negative 3 and x equals 0. If you draw that on your number line, you're going to punch out negative 3 and you're going to punch out 0. So you'll have everything up to negative 3, everything between negative 3 and 0, and then everything to the right of 0. So that's negative infinity to negative 3, unioned with negative 3 to 0, unioned with 0 to infinity, like this. So this don't simplify rule is important. If you did simplify this, and you can, this would be x minus 1 times x plus 3 over x, or x minus 1 times x plus 3 all over x. You'll notice that this guy doesn't appear to have the domain problem at negative 3. But this and this are only equal if x is not equal to negative 3. The flip and multiply trick only works if this thing is defined. This is one of those things that I usually get a lot of questions about as we dig into the homework. So I want to give you guys a minute to try and internalize what's going on there. Are there any questions about why that domain came out the way it did? Yeah, what's up, Isaac?
Wouldn't the last one be 0, negative infinity?
This guy?
Yeah.
No, 0 to positive infinity, all the way up.
Oh, I see. Okay, never mind. Sorry about that.
That's okay, it's okay. What else? Yeah, when you come to finding the domain, leave it like this. Don't simplify. If the question says simplify and find the domain before you simplify. So this would be an okay answer. Then you would use that to find the domain. And if the question additionally required you to simplify, then I would want to see you get here eventually. But it's from this form we have to find the domain. Let's try one more. I'll take this next one from your homework. That's a good one. We'll get to those in a minute. Let's look at number 10. 2 minus x squared minus 9. All right, these are both polynomials. So f plus g, f times g, f minus g, they'll all have the same domain, all real numbers. Nothing special there, right? Polynomials are defined for all real numbers. And if you add, subtract, or multiply two polynomials, the result will be another polynomial. So the fun stuff here is playing with f over g and g over f. That's 2 minus x squared over x squared minus 9. How would we find the domain here? I've got my x squared minus 9 downstairs. So he can't be 0. So I need to figure out where he is 0 and kick that out. So I solve the equation 0 equals x squared minus 9. Can solve that by factoring as a difference of squares. That's x minus 3 times x plus 3. And then setting each factor equal to 0, I find here x is equal to plus or minus 3. So from my number line, I need to punch out -3 and +3. Everything to the left of -3 is Gucci. Everything between -3 and 3 is fine. Everything to the right of 3 is also good. It's just these numbers themselves which have to go. So that would be -infinity to -3, union with -3 to +3, union with 3 to infinity. Okay. Uno más. Yeah, go ahead.
So you usually leave it by itself, but whenever you can factor it out, like whenever there's like x squared or x cubed or something like on the bottom, you have to factor in order to get like the answers separate like that, like x minus 3, x plus 3.
You wouldn't, so if I asked you for f over g, I don't require that you factor the top and the bottom, but to find the solutions to this equation, you do factor, yeah.
Okay.
Solving polynomial equations, the best way to do that in general is to factor. Sometimes you can get away, like you could add the 9 to both sides and take square roots. That wouldn't be wrong, but you got to watch out for this plus and minus. People tend to miss this. So I strongly encourage that you do it by factoring.
Okay.
I want to do one more like this, and I want to make it one of these kind of complicated guys with fractions to make sure we're good. So how about f of x is 1 over x, and g of x is x over 2 minus x squared. And let's find f over g and its domain. And let's also find g over f and its domain. F over g is f of x over g of x, which is f of x is 1 over x, and g of x is x over 2 minus x squared. And while I could simplify, I'm not gonna, because now I want to hunt for the domain. I see 3 red flags. One here, with this x in the bottom of this little fraction. One here, 2 minus x squared in the bottom of that little fraction. And one here, this whole chunk downstairs in the big fraction. So from the 1 over x upstairs, x can't be 0. From the 2 minus x squared downstairs, 2 minus x squared can't be 0, which means we factor that as a difference of squares, right? Again, so 2 minus x squared factors as the square root of 2 minus x times the square root of 2 plus x. Right? Even though 2 isn't a perfect square, it is the square of the square root of 2. So here we find that x cannot be either of plus or minus root 2. And yeah, you could have gotten that by adding x squared and then taking square roots, but again, you want to get used to factoring. And then finally, from the x over 2 minus x squared downstairs, we see that x over 2 minus x squared can't be 0. And this thing would be 0 if the top was 0. So again, x can't be 0. It's the same restriction we got from the first guy. So my domain here is everything except for positive and negative root 2 and also 0. So you can't have any of those numbers. So my domain, negative infinity to negative root 2, unioned with negative root 2 to 0, unioned with 0 to root 2, unioned with root 2 to infinity. I think maybe we don't need to do g over f. G over f would be the same shit. So you have to look around and find all of the places where the function could get angry, all of the things that could make the function undefined. And that's anywhere any fraction, big or small, is having a 0 denominator. So this guy is unhappy if x is 0. This guy is unhappy if x is plus or minus root 2. And the whole thing's unhappy if the bottom is 0. The bottom is 0 if x is 0. So we get that restriction again. That should be enough of this stuff. We've beaten this pretty hard. So the last thing I wanted to talk to you guys about this week, actually, I guess we need one more example like this. Shit. So the last thing I wanted to talk to you guys about this week are one-to-one functions and their inverses. Before that, let's do one last example with domains. This is a cool problem, and there's one like this. I can go back for just a second, but we got to keep moving. There's a similar problem to the one I just wrote down in your homework. Like this, which is a little bit fun. Playing around with square roots leads to playing with inequalities. So I would feel bad if I didn't do at least one of those for you. I'll give just 5 more seconds here. What kind of red flags are present in this function?
Square roots.
Yeah. I have 3 minus x under an even root. And x minus 2 under an even root. And both of those are going to contribute restrictions. From the first guy, I know I need 3 minus x to be greater than or equal to 0. Because those are the only sort of numbers I can take square roots of, right? Can't take square root of a negative number. I need the number to be 0 or bigger. And here, I'll need x minus 2 to be greater than or equal to 0. Neither of these inequalities is hard to solve. If I add x to both sides here, I get 3 is greater than or equal to x. If I add 2 to both sides here, I get x is greater than or equal to 2. Let's shade both of these on the number line. If 3 is greater than or equal to x, where is x? To the left or right of 3?
To the left.
Yeah, if 3 is greater than or equal to x, then x has to be smaller than 3, right? Less than or equal to 3. That's this stuff. And if x is greater than or equal to 2, that's this stuff. Then we have to take the overlap of these, right? Because I'm adding 2 functions here. I have to intersect their domains. The overlap everything smaller than 3, less than or equal to 3, and also greater than or equal to 2. That's this set. So the domain here is the closed interval from 2 to 3. Neat stuff, right? Okay. I think that's enough talking about domains. Hopefully you guys remember most of this from your college algebra, but I know college algebra varies in quality and not everybody takes college algebra. Some people come straight here from high school or straight here from years of working in a trade. So if this is intimidating to you, if you don't remember all of this, if you'd like to talk more about it, please come by my office hours. I'll sit and solve problems with you all day. But there is one more thing we got to do before I let you guys go. And it might take a little bit of extra time, so I apologize if we go over, but I'm going to ask you to hang with me and be tough here for a bit. For anybody still writing, I'll give just another 5 or 6 seconds. All right, this last topic is a big deal. But again, it's something that's covered in algebra classes before this, so I'm going to move a little bit quick. And again, if you're intimidated, come by office hours, we'll talk more. But the last topic here, section 2.8, is on one-to-one functions and their inverses. A function is called one-to-one if different inputs lead to different outputs. Okay? One-to-one functions are perfect pairings where every input has his own output and every output came from one and only one input. Algebraically, the way we say this is that f of x is equal to f of y only if x is equal to y. Or another way is to say that if x is not equal to y, then f of x is not equal to f of y. A third way of saying this is the graph of f of x passes the horizontal line test. Which is this. If any horizontal line strikes your graph in more than one place, the function is not one-to-one. Because if there is more than one place where a horizontal line strikes your graph, then what you've done is found two different x's such that f of x is equal to f of y in violation of this definition. So if any horizontal line touches the graph more than once, then the function is not one-to-one. So 3 different formulations of a one-to-one function. This function is not one-to-one because here is a pair of inputs, x and y, which lead to the same output. That's not allowed. We said f of x can equal f of y only if x and y are equal. Or if you like thinking about it this way, here's an x, and here's a y, which is definitely different from that x, such that f of x and f of y are equal. The y values along that graph are equal. Functions are often described as mappings, especially in higher level math classes. We like to think of the input space and the output space. The input space has some stuff in it. And the output space has some stuff in it. This is like the domain. This is called the codomain, but it's basically the range. And F brings stuff from the domain to stuff in the range. So maybe he brings that first guy to that first guy, this second guy to that guy. Maybe this guy goes here, and maybe this guy also goes here. So this mapping would be F. I'll call this A, B, C, and D, and W, X, Y, and Z. So according to this, F of A is W. F of B is Z. F of C is X. And F of D is also Z. And Y never got hit. Is this function one-to-one? Well, there's a difference of opinions in the chat. That's good. I like to see some debate. My no people, why is this function not one-to-one? Why is it not true that different inputs lead to different outputs?
Because two different inputs, they all lead up to, like, there's 2 points on Z. Like, it won't pass the horizontal line test.
Good, good, good. So F of B is equal to Z, and F of D is equal to Z. The two different inputs B and D both go to the same output, Z. So it's not one-to-one, fails the definition. This contradicts the definition of a one-to-one function. So no, it's not one-to-one. And it's true that this wouldn't pass the horizontal line test. If you plotted these as ordered pairs, A comma W, B comma Z, C comma X, and D comma Z, the line, the horizontal line that runs through Z would hit both points, B comma Z and D comma Z, would fail the horizontal line test. Good. Why do we give a shit? Well, let me draw another image like this, to which the answer is yes, this is one-to-one. All right. I'll start drawing down here for anybody who's still writing up there. And again, maybe I'll go A, B, C, D. This time I'll just call these 1, 2, 3, and 4. Why not? Let's make life easier. I'll call this function G. So here, G of A is 1, G of B is 3. G of C is 2. And G of D is 4. This function is 1-to-1. Because every input goes to one and only one output. Why do I care? Well, sometimes we want to reconstruct the inputs from the outputs. If I turn each of these arrows around, the blue arrows do define a function. Since G is 1-to-1, if I reverse the arrows, the result is another function. What you see is if I tried to do that back here, if I tried to reverse all these arrows, the result would not be a function because the input here would be forked to two different outputs. The blue arrows here represent the inverse function. The reversed arrows define a new function. Called G inverse, and we use the -1 superscript here. It's not a power. It has nothing to do with 1 over G of X, called the inverse. The definition of an inverse function, if f of x is 1-to-1, then a function called f inverse exists, and it is defined by the rule f inverse of anything is equal to the input that the original function f sends to b, i.e. f inverse of b equals a if and only if f of a equals b. Okay. Let me see where we're at time-wise. We're doing okay. But the truth is, I don't think I can get everything I want to say about inverse functions in here right now. So here's what I'm gonna do. Two of the same domains, different codomains to be a function, right? Yes, Isaac, the answer to your question there is yes. It's okay to send two different inputs to the same output. That's still a function. It's just not a one-to-one function. One-to-one functions are called that because for every one input, there's one and only one output, and for every one output, there's one and only one input. It's a perfect pairing. And when you have a mapping that sends things in the domain to unique things in the codomain, you can turn that mapping back the other way. That reversed mapping is called the inverse. I would love to to talk and get all the way through the content on inverse functions here, but the truth is you guys deserve to see examples. You deserve more than just terse definitions. So here's what I'm going to do. I'm going to come into your WebAssign and I'm going to extend, where are you? These two, the fourth homework and the quiz to Wednesday. Now next Wednesday is your test. That's not moving. But what we'll do is on Monday of next week, we will talk more about inverse functions. This was already set to Wednesday, okay. Do Wednesday, September 23rd. And maybe what I'll do is kind of like we did when we had that day that we lost to the holiday, Labor Day, I'll post a little supplemental material on inverse functions, how to find inverses, when inverses exist, and how to calculate them. There's a lot of neat stuff here that I want to make sure you guys really understand because it will help you understand logarithms better. And I know logarithms are never treated with the respect they deserve in college algebra, but on the way out of this class, you need to understand logarithms. The test is still the 23rd, not moving the test, just extending the homework. But I'm going to post some supplemental material for you guys on on inverse functions. And then Monday, we'll do a mixture of talking more about inverse functions and also reviewing for the test. So the test will still be next Wednesday. Exam 1, still the 23rd. The only thing I'm changing is the due date for the homework. The homework, instead of being due next Monday, is now going to be due next Wednesday to give you guys a little bit more time to learn the inverse function stuff. I'll post an additional resource in the modules. So if we come here, just like I added the even odd function stuff last week, I'll post a new module with stuff on inverse functions. And then we'll talk about that a little bit on Monday to make sure we've covered everything in as much detail as it deserves. But then the test will still be next Wednesday, okay? Now in the meantime, make sure you do all the homework problems you can. You can solve most of those homework problems. Most of them do not require anything to do with inverse functions. And I would encourage you to read the textbook and try to work through some of the inverse function stuff. It's not that hard. You can definitely answer all the questions about, is this function one-to-one or not? The only thing we haven't talked about is how to find the inverse. And for those of you who want to, I can outline that procedure quickly, but there's still more that we want to say. So given f of x, a one-to-one function, you can find f inverse of x as follows. First, write y in place of f of x. So for example, if f of x was 2x minus 1, I would write y equals 2x minus 1. Then your second step is to solve for x. So here that would be, okay, y plus 1 equals 2x, so y plus 1 over 2 equals x. And then your third step, your third step is to swap x and y. So that would give me x plus 1 over 2 equals y. And then your last step here is to write f inverse of x for y. So this would say x plus 1 over 2 is f inverse of x. Now there's more to talk about here. There are some subtle things that can happen in this step, depending on whether or not your function is one-to-one or if you have to restrict the domain. And there's all sorts of fun questions that I can ask you about points on the graph, points on the inverse, symmetries between the inverse and the original. And I don't want to shortchange that stuff. So this is by no means the end of our conversation on inverse functions. Next Monday, we will continue this conversation. And then next Wednesday will be the exam. I'll post some supplemental material that I would like you guys to look through. between now and Monday, and that will allow us to move quickly on Monday to finish the material on inverse functions, and then still have some time to review for the test. So next Monday will be a quick wrap up of section 2.8 and then review for the test. The test will be next Wednesday. You no longer have to scan and submit your study guides. Don't worry about that. Just finish them in WebAssign. And then we will move forwards from there, okay? All right, I have to go ahead and end the class here. I do have an office hour this afternoon. So if you guys want to talk more problems, you want to do problem solving, whatever, come visit me there. I will be there until 4:30. All right, otherwise, I hope you have a lovely rest of your week. Enjoy the weekend. Make sure you study hard, and I'll see you on Monday. Okay, take care, guys.